Hello everyone, welcome back to Holi-Tech Academy. So in this fifth part, we'll be discussing these topics. The topics are a problem on torque caused on electric charges, electric flux definition and its action on different surfaces, Gauss law and its applications, electric field due to infinite long straight uniformly charged area, electric field due to uniformly charged infinite plane sheet, electric field due to uniformly charged thin spherical shell. Okay, now we'll solve a problem. An electric dipole is placed at an angle of 60 degree. Say for example, if this is the electric field and these are two charges, 60 degree, this is our charge minus q and this is our charge plus q, and an electric field of 10 raised to power of 5 Newton per coulomb. E is equal to 10 raised to the power of 5 Newton per coulomb. It experiences a torque which is equal to 8 Newton meter. Calculate the charge on the dipole if the dipole length is 2 centimeter. So D is equal to 2 centimeter. Q is equal to question mark. So we know the formula for calculating the torque, which is equal to dipole moment into electric field intensity. E is equal to Q into D, that is charge on dipole to the length of the dipole. E is nothing but it is a cross product. It can be written as E sine theta. Q is equal to tau divided by dE sine theta. If you substitute the value like this, tau is 8 root 3, D is 2 into 10 raised to the power of minus 2 because it was 2 centimeter converted into meter. E is 10 raised to the power of 5 Newton per coulomb, and sine theta is 60 degree. If you calculate this, Q will be equal to 8 into 10 raised to the power of minus 3 coulomb. Now let us understand the definition of an electric flux over here. It is the total number of electric field lines crossing per unit area. Say for example, if it is our circular area, okay, if it is our circular area and these are our electric field lines and this is our normal acting like this is our normal and these are electric field lines. So electric field lines and normal are making an angle of 0 degree, right? Phi is equal to E into A, okay, which becomes phi is equal to E A cos theta because it is a dot product. Okay, dot product it always will be cos theta, whereas cross product will be sin theta. Now substitute 0 is equal to theta here, it will be E A cos 0 is 1. So it is maximum here. Now, if we consider an area which is a little tilted here, say for example, if the area is a little tilted over here, and the normal will be acting in this direction somewhere and the electric field lines will be passing like this, right? So it will be making an angle of theta. There will be some theta over here, but comparatively it will be lesser. In case when the circular surface is totally flat like this, okay, it is flat, in that case the electric field lines will be passing like this, but very less number of electric field lines will pass, whereas our normal will be acting in downward direction, making an angle of theta is equal to 90 degree. So what is the flux now? E into A, E dot A, which is EA cos theta. When theta is equal to 90 degree, it becomes 0. Phi is equal to 0. That time, which is minimum. Flux is proportional to the density of flow. How much the flow density is there, it depends on the area. Okay, it is directly proportional to the density of the flow. Flux varies by how the boundary faces the direction of flow. The direction of flow is in this direction and the boundary is this way. How the boundary faces, flux is also proportional to the area within the boundary. If the area is small, flux is also small. If the area is large, flux is also large because here, since the area is less, very less electric field lines pass. Here the area is more electric field lines pass. As we have already studied that total number of electric field lines crossing per unit area is nothing but our electric flux. It is denoted by phi, and it is a dot product of Ea, which is equal to Ea into cos theta, and it is a scalar quantity because dot product of vector quantity is scalar. You have already studied this in 11th, and the SI unit is Newton meter square per coulomb. For a closed surface, say for example, if we are finding an electric flux at this particular closed surface, okay, this surface is enclosed. For this particular surface, it is a closed integration of E into ds. ds stands for surface area. Let us understand what is a Gauss law. It requires very less calculation and it is only applicable for closed surfaces. Flux is a closed integration of E into ds for any closed surface. Now let us understand what is the statement given by Gauss. Total electric flux over a closed surface is equal to 1 by epsilon times total charge enclosed by the surface, which means total flux is equal to 1 by epsilon times the total charge enclosed by the surface. This is the total charge enclosed by the surface. Okay, this contains some charges mentioned over here. So q is the total charge and phi is the electric flux. So by the statement, phi is equal to q divided by epsilon naught. Now let us derive the expression for electric field due to a infinite long straight uniformly charged wire. Okay, so this is our Gaussian surface that you can see here. This is the Gaussian surface that is enclosed. Okay, and this is our wire carrying positive charges, and these are split into different areas. So this is our first area, this is our second area, and this is our third area. First and third are the top and bottom surfaces of the cylinder, and the middle portion is the second part. And as you can see, the normal and the electric field lines are making an angle of 90 degree over here. So cos 90 is nothing but 0. So that means flux is equal to Ea cos 90, right? So Ea into cos 90 is 0. That means flux is also equal to 0. Here phi is equal to Ea cos theta. If theta is equal to 0 degree, it is Ea. Okay, it has some value. And talking about this, it is also making an angle of 90 degree. So flux is equal to Ea into cos of 90 degree, which is equal to 0. So only in the second portion we can see there is some flux acting over here. So can I write it as phi is total flux, phi is equal to phi 1 plus phi 2 plus phi 3. So as we all know, 1 and 3 are 0. So phi is equal to phi 2 is which is equal to it is closed integration of E into ds. So this can be written as closed integration of E can be taken outside ds. The curved surface area of this particular portion, the curved surface area of this particular portion is 2 pi RL. So that's why this will be E into 2 pi RL is equal to phi. Therefore, by Gauss law, we know that phi is equal to q by epsilon naught. So substitute here, q by epsilon naught is equal to E into 2 pi RL. So we know that linear charge density is equal to charge per unit length. So charge q is equal to lambda into L. Now substitute this here. It becomes lambda into L epsilon naught is equal to E into 2 pi R L. L and L get cancelled. So we are left with E is equal to lambda divided by 2 pi R into epsilon naught. So this is an expression for electric field due to infinite long straight uniform charged wire. Electric field due to uniformly charged infinite plane sheet. As you can see in this particular picture, this is a plane sheet which is infinite. Okay, there is no end for this sheet and it is constituting uniform charge. For example, all the charges that are present here are uniformly placed. Okay, there is uniform charge which is present inside this infinite sheet. Okay, and it is enclosed within a Gaussian surface. Okay, this particular cylindrical surface is a Gaussian surface. Okay, it is enclosed by three areas. So this is the first area, this is the first area, and this is the second area, in the middle third area. Okay, as we can see that, as we know that electric flux is nothing but closed integration of E into ds, where it is also equal to q by epsilon naught as per Gauss law, where q is charge enclosed by the closed surface. Phi 1 on surface 1, that is on this surface, E is acting in this direction, normal is also acting in this direction. That means it is EA into, both are in same direction, 0 degree, which is equal to EA. Phi 2. So normal is acting in the upward direction, whereas electric field acts in this direction. It is making an angle of 90 degree, which is EA cos 90 degree, which is equal to 0. Phi 2 is acting in this direction, that is electric field intensity is acting in this direction and normal is also acting in this direction, which is EA into cos 0, which is EA. So net electric flux is equal to phi 1 plus phi 3, which is EA plus EA, which is 2EA. By Gauss law, we know that phi is equal to q by epsilon naught, which is equal to 2EA. And we know that it is superficial charge density sigma is equal to q divided by area, whereas q is equal to sigma into area. It is a superficial charge density which accounts for area. Therefore, sigma into a is a divided by epsilon naught is equal to 2e into a. Here a and a gets cancelled. We are left with e is equal to sigma divided by 2 epsilon naught into n cap, which is a unit vector. Therefore, this is the expression for electric field intensity due to uniformly charged infinite plane sheet. Now let us derive the expression for electric field due to uniformly charged thin spherical shell. Say for example this is point P. So if this is the Gaussian surface and this is a point P which is lying outside, which is the radius, which is making the radius of R, and inside the Gaussian surface the radius is small. And we know that area vector and electric field lines make an angle of 0. Therefore, EA into cos 0 for all, it will be EA itself. Okay. Outside the Gaussian surface, that means at this particular point, closed integration of E into ds, which is this vector ds can be written as E into ds into n cap. Remove the dot, it becomes cos theta. E into ds into cos theta is into n cap, where if theta is equal to 0 degree, cos theta becomes 1. So it will be E into integration of ds into n cap. Total surface area of the spherical shell, it is 4 pi r square. Therefore, by Gauss law we know that phi is equal to q by epsilon naught. Therefore, E becomes q divided by 4 pi epsilon naught r square into n cap for a spherical shell outside the Gaussian surface. On the Gaussian surface, instead of this small r, we will write capital R. That is the expression is E is equal to Q divided by 4 pi epsilon naught R R square. Third expression, inside the Gaussian surface, we know by Gauss law that phi is equal to Q by epsilon naught. So since there is no charge inside, because the shell is present outside, right? So outside there is presence of charges, inside there is no charge. Therefore phi is equal to Q divided by epsilon naught. So if Q is equal to 0, that means phi is also equal to 0. That means electric field intensity is also equal to 0. The electric field intensity due to a uniformly charged thin spherical shell for outside, inside and on the surface of the Gaussian surface. Now let us solve a problem. A point charge of 10 microcoulomb is placed at 5 centimeter above the center of a square. As you can see in this particular picture, this is the center and this is the charge Q, which is having the magnitude of 10 microcoulomb, which is equal to 10 into 10 raised to the power of minus 6 coulomb. And they have asked us to calculate the electric flux to the square. And this is acting only on the bottom surface. So that time we can say that phi is distributed along 6 surfaces. For single surface, bottom, phi is equal to 1/6 of total phi, which is 1/6 of Q divided by epsilon naught. Phi bottom is equal to 1 by 6 of Q is 10 into 10 raised to the power of minus 6 divided by epsilon naught is 8.854 into 10 raised to the power of minus 12. If you calculate this, this will be 1.88 into 10 raised to the power of 5 Newton meter square per coulomb.